Hey guys, in this video we're looking at rational functions. This section is a little bit challenging. It's graphing. It's got about 6 or 7 steps to get these things graphed, and so the first half of this video will be kind of going through the different pieces that we look at to get it graphed, and then the second half will be either getting the equation from the graph or graphing based on an equation. So first thing we're going to look at is the domain for rational functions, and we've seen this back in chapter 1, and basically it's that we don't get to divide by 0. So any of these I can just kind of look at them and go and set the denominator to 0 and then solve whatever that result might be. So looking at this one, I'd have 2x plus 7 equals 0. I kick my 7 over and divide out the 2, and we get negative 7 halves. And so what that is it's the bad number for the domain. So either x can't be negative 7 halves, or if they ask it the really dumb way, and I can't remember if they do or not, but it would be negative infinity up to negative 7 halves union negative 7 halves to infinity. So that's the really hard way to say not negative 7 halves. This next one, so we got this denominator that's a little bit more complicated, so let me show you how to factor that in case it's been a little bit since you've done magic method. And there's more than one way to factor this. The one that I prefer is magic method, as I referred to it. And if you have a way that gets this done like AC or the bit with the box, that's totally cool. You don't have to do it this way, whatever gets it factored. If you don't have a good method and you've been doing the guessing and checking thing and just trying it until you get the right combination, in that case you might want to loop back to the Math 094 videos. It's 5.3 is the one that you'd want to check out if you want to see a few more examples of this method. So what we do is we take and we go 5 times 39, and that's a big number, so I'm going to instead go 5 times 39 and figure out what 39 is going to be. 3 times a 13, and I'm looking for two numbers out of these that I can make that multiply back to this, which any of these do, that are 2 apart. And so right there I can kind of see if I group it as a 15 and a 13, and I make my 13 negative, then they'll still multiply to what the ends are, but add to that positive 2 in the middle. And so then what we do is we go 5x, and we toss our numbers in, plus 15 minus 13, and then I have an extra 5 going on, right? And then so that's kind of this magic step of magic method. With this, we don't have to care where we put stuff. We just divide that extra 5 right back out, and then everything lands where it should. So it's kind of a nice method for factoring. And then once I have that, I have x can't be negative 3, and then the same way I solve this, x can't be 13/15. And for this one, so this one I'm doing, so you know, it looks like a not negative 2, and it is. If we look at the numerator though, there's that temptation, oops, that should be at 2, x plus 2, x minus 2 over x plus 2. It kind of leads to the question of, well, should I cancel and then is the domain all real numbers, or should I do it as is? And the answer is to do it as is. The domain, even when you reduce, you'd have to do a variable restriction. So if I did the reduced form of this, I'd say it was x minus 2, but I'd have to have a variable restriction saying x cannot be negative 2 because this and that have to have the same domain. We can't reduce it and then change the nature of the function. So we always want to do domain prior to reducing. So this one is x cannot be negative 2. So a while now we've been saying, okay, we can't divide by 0, it's undefined. And what that looks like graphically is that we get a vertical asymptote most of the time. There's an exception, I'll show that an example down here. And so anytime we have that division by 0 situation, that's going to get us a vertical asymptote when we're looking at the function in lowest terms, so that is the reduced form. What happens to that reduced one, I'll show you down here in 2D. So here the directions are find the vertical asymptotes and the location of any holes, that's that one where it reduces, in the following functions. So, and vertical asymptotes is far too many things to spell, so I'm going to refer to those as VAs for pretty much the rest of the section. And it's going to be here the same as the domain because this doesn't reduce. So our domain, we would say x can't be 6, and the reason for that is because x equals 6 is our vertical asymptote. So it's going to be some line on the graph where the graph does some kind of crazy thing where it's going up and down perhaps. A couple of different things can happen there. But it means we're going to have some break in the graph where it does kind of crazy stuff. For 2b, if I try to solve this, and again it goes with domain, if I say x squared plus 4 equals 0, I can't factor that. And if I try to solve it, what ends up happening is I get imaginary numbers. I get plus or minus 2i. And so what this means is the domain is all real numbers, and this has no vertical asymptotes. For this one, we just want to factor. And so this is going to go x plus, multiplies to 24, adds to 11. So x plus 3 and x plus 8. So in that instance, our vertical asymptotes are going to be at x equals -3 and -8, because those are the numbers that aren't in the domain because of the VAs. And then this last one, so x minus 5, and we get x plus 5, x minus 5. So if I do, if I write this in lowest terms, these would reduce, and I get x plus 5. So the vertical asymptote is going to be x equals -5. So then that kind of brings up the question, what happens to these ones that I reduced out? That's going to be a hole in the graph. And so what happens is the graph is, the one I had back, let's see where to go. The one I had back here, if we graphed this function, and you can try it in Desmos, there's a link under additional resources. It's a really nice graphing utility, and you might find that helpful in this section just to kind of see how these things draw out. And if you look under additional resources, it's there, or you can go Desmos lowercase.com, and that's a really nice online graphing utility that's kind of handy for seeing how these things work. But so with this one back here, when I reduced, I would get this line x minus 2, right? So that would just be starting at -2 and then kind of going up. You would have an intercept, in theory, at 2. The bad number in this was -2, and so what that means is if we come out here to -2, there would be a hole right here in the graph where it wasn't defined. So if we graph this one, and you click on -2, it'll show that it's undefined right here based on this function. Other than that, it looks identical to this line, but that's why we have to have the variable restriction. So for this one, if I want to find the location of the hole, well, I know where x is because it would be at x equals 5, because that's the thing I simplified out for the reduced form. And then to find the location, I just plug the 5 back into the reduced one, because if I plug it back in here, right, I get 5 squared is 25 division by 0. But if I plug it into the reduced one, then I get 1 over 5 plus 5, or 1/10. And so what that means is I have a hole in the graph at 5, and y is 1/10. Okay, so next up is the horizontal and the oblique asymptotes. And so again, an asymptote, we saw it in logarithms, and exponentials. It's a line that the function is going to approach. With verticals, it cannot cross those. Those are absolutely positively what they are. But with horizontal and obliques, they're a little bit more forgiving. They can be crossed, but what they show is sort of the long behavior of the function. So for instance, I'll just toss down here 1 over x, y equals 1 over x. So the graph of that one looks like this. We saw that back in chapter 1 for a second, I think. And there's a vertical asymptote right here at x equals 0. And so you can see the graph's doing kind of crazy where it's going up and down. But then this one also has a horizontal asymptote, because if I try to find the x-intercepts, let y equal 0, and you can't solve it, it has no x-intercepts. It never crosses the x-axis. So this is a horizontal asymptote, and this one up here is a vertical asymptote. And so horizontal asymptotes are based on the degree of the numerator and the denominator of the function that we're looking at, the rational function. And so if I have something like, and this all makes it seem really complicated, but I'll jot some easy things here to try to make this a little bit more understandable, a little less mathy. If I have something of the form x over, actually it doesn't even have to be that, 1 over x. So for this one, the degree of the numerator is smaller than the degree of the denominator. And so this is our n over m. So if n is less than m, if the numerator is smaller than the denominator, which I like to refer to small over big, just because it's easier to remember, then we're going to get a y equals 0. And that's just like this one where we got this line y equals 0, which is this magenta line through the x-axis. If I have where they're the same, so say I have 2x squared over 3x squared, for large values of x, right, like say if, we put in something 1,000 and x is now 1,000,000, this is 2,000,000 over 3,000,000, they still reduce out and it still reduces down to 2/3. So in this case, it's going to be the ratio of those leading coefficients, or y equals 2/3. And then if it's big over small, so that would be something like x squared over x, then that's where we're going to get this oblique, which means we're going to get an asymptote that actually travels not perpendicular, or not parallel or perpendicular to the axes. It'll be some sort of linear one. So let me show you that with some real examples. Oh, one more thing. Sorry, one more thing back here. The other thing we're going to do is determine whether or not the horizontal or oblique asymptote is intersected by the graph. And to do that, all we got to do is set our asymptote equal to the original equation. And so if it is intersected, we'll have a solution. If it isn't, then there's no solution. We'll see that later when we do the graphing. Okay, so for these next ones, we have, for the following functions, find the horizontal and oblique, or I think this book might call them slant asymptotes. I'm used to saying oblique, so I'll keep saying that. And check to see if it's crossed. Okay, so if we do, for this one, it's going to be the power of the numerator is 1, the power of the denominator is 2. And so this is what I refer to as small over big. In other words, we have a smaller power on top, bigger power on the bottom. And this isn't, obviously official math speak, but it's a nice, easy thing to kind of help you remember it, hopefully. And in that instance, if you look back at the little table on the last page, we get y equals 0. So if I want to see if that is crossed, then what I can do is I can set the original function equal to the asymptote. So 0 equals 3x, and then x squared minus 6. Multiplying that up, so I'm going to clear the denominator by multiplying both sides. Those cancel. That's still just 0 equals 3x, because 0 times this is still 0. And then dividing over 3, I get x equals 0. So that means that our asymptote is crossed at the origin. So crossed at 0, 0. For this one, so this is same over same. So x squared over x squared. And so in that case, it's the ratio of the leading coefficients. And I did the sneaky one kind of on purpose. These are both 1s. And so in this case, our asymptote would be y equals 1. So 1 over 1. If I want to see if it's crossed, I can say 1 equals x squared plus 4x plus 4 over x squared plus 8. And now I can multiply both sides again by x squared plus 8, x squared plus 8. Those drop out. And now I'm left with x squared plus 8 equals x squared plus 4x plus 4. So since both sides have x squareds, I can cancel those. It's the same as if I subtracted it over, because it would just be 0. And now I'm left with 8 equals 4x. I'll subtract my 4 over. and I get 4 is equal to 4x, or x is equal to 1. And so this one is crossed at 1, 1. Oops. Ignore the blob. Okay, so then this one, this is big over small. And that's where we get the oblique asymptotes. So it's the square over the first. And so to get the oblique, it's kind of a bummer. We have to do long division. Well, there's actually another alternative, but I'll show both forms. So here we're going to do, what do I multiply x by to make it x squared? That would be an x. And then x times x is x squared. X times negative 2 is negative 2x. Those drop out. 7 minus negative 2 would be positive 9x, and then minus, we bring down the minus 5. And then we're at, what do I multiply x by to make 9x plus 9. And then I could finish it out from there and get to the remainder, which I guess I'll go ahead and do that. It ends up not mattering, but let me show you how come it doesn't matter. So 9x, and then that's minus 18. And minus a negative 18 makes positive 13 here. So what I got for my answer for my division is x plus 9 plus 13 over x minus 2. So the reason the remainder doesn't matter is because if I let x get very, very large, like if we're going to infinity, or very, very small going to negative infinity, 13 divided by a million is pretty much 0. So for long-term behavior of this thing, it's going to approach x plus 9 because this piece goes to 0. And so our oblique asymptote is going to be y equals x plus 9. So it'd be a line with a slope of 1 starting at 9 up there and continuing to infinity. And then to see if this one is crossed, what we'll do is we'll go, we're going to set the function to the oblique asymptote. So that'll look like x plus 9, and then can that equal x squared plus 7x minus 5, and then x minus 2. So I'll do that same thing where I clear the fraction, so we multiply both sides by x minus 2. Those cancel. Over here I'll do a little bit of FOIL, so I'll be x squared, and then plus 9x minus 2x minus 18 equals this stuff up here, and let me collect my terms and I'll bring that down. X squared plus 7x minus 18 equals this x squared plus 7x minus 5. So now if I try to go and solve this, I would bring over, I'd try to get, my everything over to one side. If I brought over the x squared to bring my x's to one side, and I'll bring over the 7, all this ends up dropping out, and so I end up with negative 18 equals negative 5. And so that is not true. That's a no solution. And so what that means is it is not crossed. So you get some false statement like that if basically a no solution problem if the asymptote isn't crossed. Okay, up next is x and y intercepts. So for the following problems, find the x and y intercepts. Remember, to find a y-intercept, we just let x equal 0 and see what happens. To find the x-intercepts, we're going to let the y side, the r of x equals 0, and then solve for x. So for the y-intercept, let's see what happens there. So if I let x equal 0, and instead of r of x, I'm going to call it y, just because we're talking about intercepts in order pair, and I think it's more comfortable with the y. We're just going to go 3 over 0 plus 5, or that makes 3/5. So for here, the y-intercept will be 0 and 3/5. And then to do the x-intercept, I set this side to 0, so I let y equal 0. And then when I go to try to solve that, you can see what will happen here. X minus, or plus 5, x plus 5, cancel. 0 times this is still 0 equals 3. So again, a false solution, and so that means there's no x-intercepts. Same thing with this next one. So if I let x equals 0, right there you can kind of see I'd have 0 plus 11 times 0, and so that is going to give me division by 0. So when I let x equal 0, it comes out undefined. So what that means is there is no y-intercept. And then to do the x-intercepts, I'll go 0 equals x squared minus x minus 12. And right here, I'm just going to kind of show this thing so we can kind of shortcut the x-intercepts from here on out. If this side is 0, what I'm going to end up doing is multiplying by 11x on both sides. And so that always cancels out, and you're left with 0 equals the numerator. So to solve these a bit more shorthand, I have it right here. Set the numerator to 0 and solve, and that's going to be the same thing as your x-intercepts. So I can just kind of shortcut to there. And then 0, this would be multiplies to negative 12, adds to be negative 1. So x minus 4 and x plus 3. And then that's going to give us intercepts at 4, 0, and at negative 3, 0. And I encourage you, as you're kind of doing your scratch work on these problems, to write these as ordered pairs. People have kind of floating 4s and negative 3s around, and then sometimes it melds into a 4, negative 3, which has nothing to do with the x-intercepts. That's totally wrong. So be cognizant of the fact that you're letting y equal 0, and that this is, these points, right? 1, 2, 3, 4, 1, 2, 3, that are on the x-axis. Okay, for this next one, find the x-intercept. So I let 0 equal x minus 5. Sounds pretty easy. I bring this over, and I'm going to get 5 equals x. So in other words, the x-intercept is at 5, 0. And then for the y-intercept, I'll let x equal 0. So 0 minus 5, 0 squared minus 4. And so I get negative 5 over negative 4, or 5/4. So my y-intercept is 0 and 5/4. Here, let's see. So we'll set our numerator to 0. And here you got to remember the cube formula factoring. And if you haven't done a sum of cubes for a little bit, or a difference of cubes, 094, and it's section 5.5 is the video that you can use to kind of review this. So, and that's on my YouTube. With this, we're going to go x equals, and this is a cubed plus b cubed, and those factor to a plus b, a squared minus ab plus b squared. And so hopefully you already know that. This is going to go x plus 2, and then x times x is x squared, x times 2 minus 2x, that's our AB, and 2 times 2 for 4. Again, go back here and review if you haven't done a cube for a while. This piece of the cube always has imaginary solutions, so we don't need to worry about that for our x-intercepts. This piece is the piece that's going to actually get us something. So this would be x plus 2 equals 0, so x equals 2. And if you do try to solve this, you could do quadratic formula or completing the square. But again, it's not going to get you anything useful because it'll have imaginary zeros. And, a way that you can know that is if you think about what x cubed plus 8 looks like. So x cubed looks like this thing, right? And then it's just been shifted up 8. So it's still only going to have one intercept. Oops, you know what? That should be negative 2 as I'm looking at that graph. Yeah, I caught that. So this is just shifted up 8, and then this piece is crossing right there. And so that can kind of help you get your mind around that this piece isn't contributing zeros. And then we still need to get our y-intercept, so let me do that. Our y-intercept is going to be, so if the x's are 0, it's going to be 8 over negative 25. So that'll be 0 and negative 8/25. Okay, so that was all the pieces, and now we're going to start trying to write, or we're going to go two directions. Given a graph, write the equation, or even just a verbal description of the graph, write the equation. And then after that, we're going to actually graph these based on an equation. So, writing a rational function from the intercepts and asymptotes, or a graph. So, I have this thing here, and this is a really helpful deal if you can kind of get your head around it. So let me start. Zeros from the numerator are x-intercepts. Okay, so we saw that when we were solving for the x-intercepts. So whatever these zeros are, that gives us where we are crossing the x-axis. And then just like back in section 3.4, even powers bounce. And so, you know, if we have something coming down and touching, it's going to do this. And odd powers cross. So that's consistent with these. Zeros from the denominator are the vertical asymptotes. And so we saw that at the start of this section, that any place we have division by zero is in reduced form, it's going to give us a VA. So then the behavior of the VAs, that's going to be these two pictures. So if it's an even power, it looks like 1 over x squared. And for what I was using, I couldn't get a good math typeset on that. So 1 over x squared. For an odd power, so this is even powers look like x squared, odd powers look like 1 over x, because that's to the first. And so for odd powers, they kind of go off in opposite directions is the deal. Even powers, they're going to go off in the same direction. And so in class, I always kind of joke that, so this one's single, so like they got a divorce. These two, there's two of them, they're married, they go off together forever. So the squared one's married, x to the first, or any odd one, that's divorced. They're heading their separate ways. So that's what we're going to be able to tell based on those powers and those. The last thing is a stretch factor. So we can have a value out here in front of the equation that does the vertical stretch, the same as we saw back in 1.5. And a lot of these ones are going to be for the find the equation, we're going to be solving for that stretch factor. So let's see what that looks like with an example. So number 5 is write an equation for a rational function with vertical asymptotes at x equals 2 and negative 4, at x-intercepts at x equals 3 and negative 6, and then a y-intercept at 6. So our y-intercept, that's going to be 0, 6. And I'll show you what we're going to use that for in just a second. So just to kind of recap back here, and this is page 84 in the notes, and again, this is a pretty helpful diagram for getting these things figured out. So our x-intercepts are our numerator, our vertical asymptotes give us our denominator. So looking at what they gave us, vertical asymptotes at x equals 2 and x equals 4. So we'll set this up as y equals, and then there's that stretch factor that we got to figure out, and we're just going to let a represent that for now. And we're going to have downstairs our vertical asymptotes. So if x equals 2 is a vertical, then x minus 2 is the factor it came from, because they're just going to have the opposite signs. Likewise, x minus 4 is the asymptote, then x plus 4 is the factor, because that's what would have made that 0. And at the x-intercepts, we have x equals 3, x equals negative 6. So same thing, opposite signs, x minus 3 and x plus 6. So that gets us pretty close, but then there's still now the stretch factor, and that's where the y-intercept comes in. So now I have in this equation, I have x's, a y, and an a, and this is an x and a y, so that means that's enough that I can solve for a. So we're going to plug this in. Y is 6, a is what we don't know. All of these are just going to be zeros, so I'm just going to write this negative 3 times 6 over negative 2 times 4. And now I can just solve this, because that's all those just being zeros, so the x's drop out. I can solve this for a, and then that's going to give me my final equation. So we got 6 equals, that would be a negative 18 over a negative 8, so I'm going to drop those signs since it's a negative over a negative. So 18a over 8. If I do a little reducing there, I could knock a 2 out of both those. So let's make that one a 9. We'll make that one a 4. And actually, you know what? It's better if I don't. I just looked at what's coming up. Scratch that. Let's leave it 18a over 8. I'm just going to throw my 6 over here because that all got a little messy. If I reduce it, I'm going to have to do a little bit of extra math. I just saw this 18. So I'll do instead is I'm going to multiply both sides by 8 over 18 because that's going to knock this out. And then the 18 and the 6 play nice. So that's why I was saying, let's just leave that in 18 for now. And so that's going to equal A. And then A is, I go 6 goes into 6 once, 6 goes into 18 3 times. So A is 8/3. So final answer on this would look like y equals, and rather than writing 8/3 up in the numerator, which looks kind of crummy because there's a fraction in the fraction, we'll write it 8 over 3, x minus 3, x plus 6, and x minus 2, x plus 4. Same basic thing, but now instead of a y-intercept, we're given a horizontal asymptote, which is actually totally better, and I'll show you how come in just a second as we get to that spot. So this is going to be y equals a. My x-intercepts are at 1 and -2, so x minus 1, x plus 2. And they're not saying multiplicity 2 or anything, so I just know they're to the first. And my verticals are 3 and -3, so I'll be an x minus 3 and an x plus 3. So then the deal with the vertical asymptotes, the horizontal asymptote, if to get a horizontal asymptote of y equals 5, that's got to be that kind that was same, for that to work out. If you look, there's our x squared, and so this has to be 5 over 1, or I don't get a horizontal asymptote at y equals 5. So pretty much what that means is a is 5. And so that's what I was saying, this one's a little bit easier if you can just kind of get past that little piece. So x plus 3, x minus 3. Okay, so now we got a graph, and we're doing the same idea. We're trying to figure out the equation based on this graph. So that's where this is pretty handy again. So I'm going to do the same thing. I'm going to look for my x-intercepts. That's going to make my numerator. But now I have to be careful that nothing's bouncing or crossing, and that's going to tell me my powers. And then likewise vertical asymptotes, and I'm looking to see if it looks like this or like this, and that's going to tell me my powers on there. And then we're still going to have to try to find that A. So that will look like A, and then I have intercepts at 3 and -3 and 3, so it'll be x plus 3, x minus 3. And I have verticals, if you can see them on here, this looks to be -2 and 5. So x plus 2 and x minus 5. And that should equal y over there. So then I have to check and see if anything is squared. Crossing at the x-intercepts, so those are both to the first. And then if you look, so if we think of the sort of married analogy or divorced, that one's getting divorced, right? Because they're heading their separate ways. This one's also getting divorced, heading their separate ways. So everything is to the first, and now they gave me that nice y-intercept there. I can plug that in for my x and my y and use that to solve for the a. So 2 is going to equal a, and I'll just do the same thing where I go 3, -3, 2, and -5. So that's going to make 2 times double negative again, so positive 9a over 10. And then I'll multiply both sides by 10/9. And that's going to get me 20 over 9 equals, cancel, a. And so my equation is going to look like y equals 20/9 x plus 3, x minus 3, x plus 2, x minus 5. Okay, another one of these. So let's get our everything kind of set up, and then we'll figure out our squares. We're going to have y equals, we have an intercept at 2, so that's going to be x minus 2. Let me get my a out there. And then on this one, check it out. So it's coming up, it's bouncing, it's turning back around. So that tells me that has to be squared. Because remember, even powers bounce and odd powers cross. For my vertical asymptotes, it looks like I have one here at -2, so that's x plus 2. And that one is at 3. So x minus 3. And then on the 3 one, they're heading opposite directions, right? So that's the divorce. They're to the first. They're alone. They're 1. But this one, you see how they're heading? So I extended this out, right? They're going to keep getting closer and closer to that line. So they're going off together. So that one is the married one where there's 2 of them. And then we have a y-intercept again, so I can use that to solve for my a. So -2 for y equals a. And then this will be -2 squared over 2 squared times -3. So -2 equals, let's see, that's going to go 4a over, and this will be 4 times -3, so that is -12. I think I will go ahead and reduce that. So -2 cancel makes -a over 3. And then here I can just multiply both sides by -3. So that is 6 equals a. So final on this, since that's pretty messy up there, it'll be 6 and then x minus 2 squared over x plus 2 squared and x minus 3. Okay, so we've arrived at actually graphing a rational function now. So our steps are going to be factor the numerator and denominator of r, which is the rational function, and then find the domain prior to reducing. And then we're going to write r in lowest terms. So if it does reduce, everything else below this is kind of happening after the reduction. And if we have something that reduces, remember that if something cancels out, that means that's going to be a hole in the graph, and we're going to have to go find that. So we write r in lowest terms, find the x and y intercepts, find vertical asymptotes. We're going to find the horizontal or oblique asymptotes. We're going to set the horizontal or oblique equal to the function and see if it's crossed. And then after we do all that stuff, we're going to use all that information to graph the function. So let's see that. So let's see that with an example. So we'll factor our numerator and denominator first. So r of x is going to equal x plus 1, and then x minus 4 and x plus 1. So this cancels. So my reduced form on this is going to be 1 over x minus 4. But I can't just kind of disappear that and have it not count. What that's going to do is give me a hole in the graph at, I'll do it up here, x equals -1. And so then if I plug -1 into the original, into the reduced form, if I plug it into the original, I just get division by 0. So I plug it into the reduced form, and that gets me y equals 1 over -1 minus 4, or -1/5. So we're going to have a hole at -1, -1/5. And so now we got our reduced form, and so we can find the rest of this stuff. So I've done step 1, factored it, found the hole if it existed. Step 2, write in lowest terms. And now we're doing x and y intercepts, vertical and horizontal asymptotes. So, and we're doing that with this reduced one, which is nice. So for the reduced one, oh, I didn't actually say what the domain was, I'm sorry. So the domain is x cannot be 4 or -1. -1 is going to be a hole, and then the 4 is going to end up being our vertical asymptote in a second. So for step 3, this was kind of step 1, This was kind of step 2. And then step 3 is find the x and y intercepts. So if I let x equal 0, I have 1 over 0 minus 4, or negative 1/4. So that means my y-intercept is 0 and negative 1/4. Like that. And we have a hole right there. My x-intercept doesn't exist, because if I set y equals 0 and try to solve, and I just have to set the numerator, you can see I get 1 equals 0, so no x-intercepts. Let's see, 4 is find the verticals. So vertical asymptotes are going to be at anything that wasn't a hole, that or the zeros in reduced form. So we're going to have a vertical at x equals 4. 5 is find the horizontal asymptote. And so if we look back, this is going to be small over big to include the reduced form. So that means our horizontal is y equals 0. To check and see if that's crossed, I would set 0 equal to the 1 over x minus 4, which is what I just did here for the x-intercept, and it didn't work, so we can say not crossed. And then that was step 6 right there. So then step 7 is to take all that mess I just did and try to turn it into a picture. So we got a little bit of information here. Let me change colors. So I'll do vertical asymptote at 4. So that's going to be right here. Horizontal asymptote at y equals 0. So that's the x-axis. I don't have an x-intercept. I do have a y-intercept right here at 0, negative 4. So I'll just kind of put that about there. And then I have a hole in the graph, where was it? Negative 1 and 1/5. So that is hard to graph, but it's basically right there. So then, what we can do to get the rest of the graph is pretty much just kind of deduce it from the information I have. This is actually enough to do it all. The horizontal asymptote, remember back down here on number 6, was not crossed, which means this thing, since it's below the horizontal right now, it can't get back up above there. We would know about it if it did, because I would have found an answer here. So this is just going to approach from the bottom, and then here it never can cross a vertical, so it's going to kind of head off to infinity that way. And then there's kind of 2 things that could happen. I could have graph down here, or I could have graph up here on the other side. And so if we go back to this, and this is where this stuff is really nice because it saves you a bunch of doing like test points. If we look at this asymptote, it's x minus 4. It's to the first. Anything to the first, that's the divorced one. They go their separate ways. So that tells me, without even having to test a point, that my graph has to be something like this. And we're not trying to get these really exact. We're just trying to get the right kind of shape. So this is totally adequate for that. Okay, so first thing, we get this thing factored. So out of the numerator, I would pull a 2. It'd be x squared minus 4. And I'll sneak down here with it from there. So this will be 2x plus 2, x minus 2. And this multiplies to negative 5, adds to be negative 4. So that'll be x minus 5 and x plus 1. So that is in lowest terms, so I don't have to reduce anything. So that was kind of steps 1 and 2 right here. Step 3 is find the x and y intercepts. Let's do that. So the x-intercepts I can grab right here from the numerator. So remember, to get x-intercepts, we just set the numerator to 0. So my x-intercepts are going to be negative 2, 0, and 2, 0. My y-intercept is easier to see from the non-factored version because I can just cover up all the x's because they're all zeros, and it leaves me negative 8 over negative 5, so that's positive. So y-intercept is going to be at x is 0 and y is 8/5. So that's another clue. Step 4 is find the vertical asymptotes. So that's the zeros in the denominator. So my VAs are going to be at x equals 5 and -1. My horizontal asymptote, again, when I come back to the original, this one is the same, they're both squared. So my HA is going to be the ratio of these leading coefficients, which would be y equals 2. And then we need to look and see if that is crossed, and that's step 6. So we go 2 equals 2x squared minus 8 over x squared minus 4x minus 5. And so I'm going to multiply both sides by x squared minus 4x minus 5. Same thing over here. I didn't write that very good. Let's see. We'll just go x squared minus 4x minus 5. And we multiply that by 2. Sorry. So that's going to go 2x squared. And then 2 times 4 makes minus 8x. 2 times -5 for -10. And now those canceled, so it just equals the 2x squared minus 8. If I go to bring my 2x squareds over, it's going to reduce out and be 0. So you can always do that when you have the same thing on both sides. And then that leaves me -8x minus 10 equals -8. Add the 10 over. -8x equals 2. And then x equals -2/8 or -1/4. And so it turns out this one is crossed. And the y coordinate on that, remember what we did was we set it equal to y equals 2. So that's the y coordinate, because we're looking for, does it cross at 2? Yes, at -1/4. So we're going to say crossed at -1/4 and 2. So that's all of our information, and now we just have to try to draw that in some sort of cohesive looking graph. So let's see. We got lots of asymptotes this time. We got one at -1. We got one at 5. And we have y equals 2. So there's our asymptotes, and then let's get all of our intercepts sketched in, and that's going to give us a bunch of information. So x equals -2 is an intercept, x equals 2 is another intercept, and then 0 and 8/5. 8/5 is about 1 point, not about, it is 1.6, and so that would be right about there. And then lastly, we know that our horizontal asymptote is crossed at -1/4, 2. So -1/4 would be a bit over from the x-axis and up here at 2. So that's kind of all the information we have. And then this is where, again, this is like super helpful, because otherwise it's really confusing as to what might happen. You end up doing all these test points. If you look in some books, they'll have you just start plugging points to see where stuff is. And we can be smarter than that. Because we know we know about the vertical asymptotes. These are both to the first, and actually everything is to the first. So nothing is bouncing, everything has to cross, and then these verticals have to head off in opposite directions. And that's going to give us enough information to get this thing graphed without doing any sort of test points. So up here, we're going to cross through the asymptote, the horizontal, and then come down here, and things don't bounce off of asymptotes. It's a crossing situation, and then we know we have to hit this point, and this isn't a bounce, it's a cross, because this is to the first. So then the only thing this can do is go up, or sorry, go down. Over on this side we have an intercept, and we know it's not bouncing, it's not doing any of that. We can't cross a vertical, so it has to be going this way. And so there we see that to the first behavior, where this side's going up and this side's going down. And then over here, it's going to approach the asymptote. So then how do I know it doesn't like go up and do something crazy? Because we checked to see where it was crossed. The only point is right there, so that's its only choice. So in this third third kind of quadrant that we're looking at. This side's heading down. These are to the first. Well, the fifth is to the first. So this side has to be up. It has to, because that's what 1 over x does. So without even testing a point, now I know there's that piece of the graph. And that would be complete. So then we saw the kind that had a horizontal asymptote at 0, which was small over big. We saw same. So this one's going to be big over small, where we get an oblique. So first let's write this in factored form. So that's going to be x minus 10 and plus 3. So multiplies negative 10, adds to positive 3. So x plus 5 and x minus 2. And then x plus 3 down there. And so nothing reduces, so there's no holes. I think I forgot to find the domain on that last one, but that's okay. The domain on this would be not 3. And really the domain where you care about that is if it's going to have a hole, so if it doesn't reduce, the domain isn't that exciting, but not negative 3 here. So then it's already in reduced form, so that was step 2. Step 3 is our x and y intercepts. So we're going to have x-intercepts at negative 5, 0, and 2, 0. And then looking at this form is easier for the y-intercept. So if I just cover up all the x's, these things on the end have to be the y-intercept. So that's going to be at 0 and negative 10 thirds, or about negative 3.3 for graphing purposes. Our vertical asymptotes, that's going to be x equals negative 3, so that's our bad spot in our domain. And then the horizontal oblique, well, this one is big over small, so this is where we have to do long division. And I think I forgot to show synthetic division back in that last example, so I'll do that here. X plus 3, I'll do the long division version first, and then I'll do the synthetic. So we do, what do we multiply x by to make x squared? That would be x, and then x times x is x squared, x times 3 is 3x. And then we do our little subtract, and this is nothing, minus 10, and x doesn't go into 10, so it would be, if we were going to write this with a remainder, it would be x minus 10 over this, but this goes to 0. So our oblique is going to be the line y equals x, or just that parent function for all lines. Synthetic division, which I mentioned, that's the thing where you do, since this is the factor for synthetic, we use the 0, so it's negative 3, and then we do 1, 3, negative 10, and bringing down my 1 is the step that we do. Negative 3 times 1 is negative 3. There's our 0. Negative 3 times 0 is 0. Negative 10, there's our remainder. And so if you remember when you're going x into x squared, this is always sort of 1 degree less. So this is x, and then it's that same minus 10 over x plus 3, but this all goes to 0. So same thing there. If you need a little bit more help with long division of polynomials, if you don't remember that from 98 or 95, I think I have an 095 video up, and that is, which section is that these days? I believe it is 7.7095 is the one that you want to look for, and that's in the newer 095 videos, not the older ones. And in that I do long division and I do synthetic on several examples, so you can see a few more versions of that if that's not something you remember how to do. The other thing we need to do is see if our oblique is crossed. So we're going to set x equal to x squared plus 3x minus 10 over x plus 3, and we will multiply both sides by x plus 3. And those cancel. X times x, x squared, x times 3, 3x equals x squared plus 3x minus 10. And if you look right there, those are all dropping out. 0 equals negative 10, so not crossed. Which still gives us information. It tells us it has to stay on one side or the other. And then we'll draw it. So we got the line y equals x as our oblique asymptote. That's going to just kind of cut diagonally right here. And we have a vertical asymptote at -3. And we have x-intercepts at -5. That's right there. And at +2. That's right there. And we have a y-intercept at -10/3, which I said is approximately -3.3 for graphing. So there's 3 and about 1/3 right there. So what that means is, so we have this vertical, and so we basically, each vertical asymptote is kind of giving you a boundary of where you need graph. So this side is going to look something like that, where this is going to keep trailing in forever. We don't need anything up here because we got graph down here, so that's covering everything on this side. Likewise, I don't need anything down this quadrant because this point is telling me that this side's going to look something like this. And so that fills in my whole domain. The only place I don't have graph is on the -3. Okay, so hopefully that is the longest video of the quarter. That concludes rational functions.